evolutionary robotics. So we're going to talk about some of our experience from the University of Oslo in doing this, and trying to give you a bit of an intro to how to evolve robot brains and bodies. And we're especially considering here robots that adapt both their morphology and others their body and their control at the same time. And those extra challenges that arise from this happening together. So the ones that will hold this tutorial is myself, my colleagues here, and Emma from the University of Oslo. Just to briefly say who we are and where we are from. So we have had a very short trip to this year's A-Life. We come from right across this body of water between Norway and Denmark. There's actually a ferry that goes directly from Oslo to Copenhagen. So I'm going on that ferry tomorrow to get back home. So we have had an easy way of getting to A-Life this year. This is where we normally find ourselves, the building of the Department of Informatics, University of Oslo, where we sit over here and do experiments on evolving robots and many other things. One more person needs to be mentioned in this presentation, which is our colleague Frank, who helped us design a lot of the content for this tutorial last year, where a similar tutorial was held at A-Life, and we have kept some of his excellent contributions this year. He is at the moment sort of in between jobs, which is why he's not at A-Life this year, but he's starting the position at Bruin University soon. So maybe he can join us next year again on A-Life. Our plan for today is to start with some theory and end with some practice. I will start by talking a bit about some of the basics of evolutionary robotics, the motivation for doing it, a little bit about how it's done, and part about representations. I won't spend too much time on that because there are many talks on evolutionary robotics already this week. So you have all hopefully been introduced to many of the basics already. Then my colleague again will go into some of the challenges that we see when we involve bodies and brains controllers together, and some of the possible solutions to those challenges. Finally, I will wrap up by talking a bit about the difference between optimizing robots in simulators and the real world, and some of the building blocks that we can build robots from. And finally, Emma will wrap up with a practical demo. Feel free to ask questions or give comments along the way. And we'll also try to have some short reminders for you that you can ask us questions between these different parts. So just slow down there a bit and see if there's any discussion to be had. But let's just start with the basics. We'll start with why we evolve robots. And for me, and I think for many of us, a lot of the inspiration for working with bio-inspired AI and bio-inspired robotics comes from the amazing adaptable capabilities we see in animals and creatures in nature. Here's an example of that. Here's a dog that was born with 4 legs, but had to amputate 2 of its legs, and found a very robust and impressive way to run around with only 2 legs. If you look at it briefly, you can almost not even notice that it only has 2 legs. And this happened after it was born. It was born with 4 legs, so it found a way to adapt very gracefully to the change to its body. And this is the kind of thing we want to see in our robots, but that current robots are usually not good at. If something unexpected happens or a robot gets damaged, it typically doesn't know what to do at all. But we hope that they will be able to do things like this, adapt to big changes to their body or environment. Another thing I want to mention is that evolutionary robotics is quite a lot about making the robots of the future. So if we're building a robot for a factory or a robot for doing a task that we have well-established methods from robotics, mathematics to solve, then we should rely on traditional robotics. But if we're building robots that we're not quite sure how to control or how to design, evolutionary robotics can be a good technique for exploring different components and explore different designs. Such as these kind of robots that move by getting air pumped into them, these kind of robots that are built from modules, and we're not quite sure how to best assemble those modules to build robots. That was a very brief motivation for why we do evolutionary robotics. Now the how of evolutionary robotics can be summarized like this. So on the left side here, we have an evolutionary algorithm. That is an optimization technique that through multiple generations, step by step, optimizes solutions to some problem we have. So an evolutionary algorithm can be used for many kinds of problems, not just with robotics. It sort of simulates the process of evolution that we find in nature, where we have a population of individuals, each represented by a genome, that fight for survival and over time get better and better adapted at solving some problems. When we have evolutionary robotics, the thing that separates it from other evolutionary algorithms is the part of here, the evaluation. So in an evolutionary robotics experiment, we have to take all these solutions we're currently evolving, the genomes of those solutions. We have to somehow decode them to get a robot design that we can evaluate and interpret that design to build an actual robot that we can test out and see how well it performs. Yes.
So in my vocabulary, the counterpart of a genotype is a phenotype.
Yes, yes.
Which block would be that on your picture?
Yeah, so the phenotype are the little last.
That's the phenotype.
The one that we can assess the fitness. And we don't necessarily have this part in the we sometimes we go always directly from the phenotype to the phenotype. Then we get some sort of a value out of our test of the robot. For example, this how fast it's walking or how well it's also tasked. We call fitness value that we can feed back to our evolutionary algorithm to serve for better and better robot designs. Sometimes we care about other things than this one value too, such as some indicators of the robot's behavior, and we'll get back to that a bit later. But that's the one slide summary of how this works. Any questions on the very high level before we go a bit more into details? Okay, so in the rest of my part, I'll talk a bit about representations. And the reason I'm going to spend some time on that is because that's one of the most central decisions we make when we do an experiment in evolutionary robotics. We have to find out how we can represent a robot in such a way that the evolutionary algorithm can efficiently search for good designs. To understand why we need to think about how to design representation, we can think of it like that. So what we need our evolutionary algorithm to, or when our evolutionary algorithm makes progress by taking some sort of a solution and making small changes to it over time. And therefore that solution has to be in a format that we can make small changes to, and that our evolutionary algorithm can adapt little by little. And that often means that we try to represent things as some sort of list of numbers or list of other things that we can easily mutate and change. So for example, if we have this list of numbers here, 1, 2, 3, we can easily mutate that to 1, 2.53. But this list of numbers is not a robot design. So to be able to translate this to a robot design, we need to find some mapping that tells us based on this list of numbers, how can we build a robot. So there's sort of a mismatch here between what we need to be able to adapt our solutions and what we need to be able to have to evaluate our solutions, which is a robot design. And that's what the representation tells us. How do we find this mapping from a list of numbers or something simple to modify to an actual robot design. There are very many ways to set up such a representation. We can't go through all of them, but I'll try to sort of tell you about the two things that I consider the main categories, and I'll give you a few examples of them. So there are two main categories to representations, or they can maybe also be other types of ways to categorize these. But two of the main ways we can divide it up is by having a direct representation or an indirect representation. The direct representation means that there's more or less a one-to-one mapping from the representation we have to the robot design. Whereas an indirect representation or indirect encoding means that there are more steps along the way. So there's sort of more of a decoding process or a step-by-step building process we have to follow to go from our genome to the finished robot. And so the main difference lies in this step here. How do we decode this genotype that we have to make it into the blueprint for building our robot? We'll see some examples to make it clear. So here's an example of a direct representation that members of our, or two different direct representations that members of our lab have worked on. One way we can set up a direct representation is to say that we want our robot to look like this. We want it to have these two pieces, these four legs, but we don't know exactly which angle those legs should be at, and we don't know exactly how long those legs should be. So we want our evolutionary algorithm to figure this out. And then we can say that this gives us a few parameters. So there's this parameter here that tells us how long should this leg be, and what should be the angle of this leg. Then we can put all those parameters in a list and say to the evolutionary algorithm that its job is to find out the best possible values for these parameters. And then it goes ahead and finds a good design for a robot. And this is a direct representation because there's a one-to-one map here between the values in our genotype and the design parameters for our robot. So to build the robot based on our genome is a quite straightforward process. An indirect encoding, on the other hand, is usually involves more work to decode the genome we're building. So here's an example from our colleague Frank's work, where there was an indirect representation used to evolve these kind of robots that we see here. And an example of how we can set up an indirect representation is that we can say that our genomes are sort of specify sort of a rule for building a drawing of a robot or a blueprint for a robot. So, for example, this genotype here, A, B, C, C, D, E, F, can be interpreted as these rules. Node A points to nodes B and C. Node C points to node D, E, and F. So this is just an example of one way to make a way to interpret genomes as rules for building a robot. And that can take us from a genotype to a sort of a graph that specifies how our robot looks if we follow a decoding like that. And then we can evolve better rules of this type by using specialized mutation operators, because typically making random changes to something like this is not going to end up with something that works. So we often want to have a bit more structured change than something random. So there's one more step we need here. So now we have went from a genotype to a sort of a graph specifying our robot. And then we need to somehow interpret this graph to build the final robot. And that's usually done with some sort of predefined mapping that tells us what its different components of the graph correspond to on the robot. For example, this element could correspond to one of these rectangular elements on the robot. Maybe this one corresponds to a circular element on the robot. And the connections between the items on the graph typically tells me about how the robot is connected. So this is maybe the main node of the robot, and a connection on the left part here maybe means that we connect this node here on the left side of the robot. And there are many ways to do this. And we can also, for example, enforce symmetries by saying that we build a part of the robot in this graph here, and then we just build the other part identical, and we get a symmetrical robot. Yeah, but this is just an example of an indirect encoding, where we go from a genotype to a finished robot involving a sequence of steps, and the genotype is more like a recipe for building the robot. So if we look at this side by side, we see that there's a quite big difference in how much freedom and we has to design the robot here. In the indirect encoding, we can find sort of any type of recipe for building a robot that the genotypic representation allows. We can explore many different robot designs. Whereas with a direct encoding like this one, we have done a lot of the job designing the robot already, and the evolutionary algorithm finds out some details. So there are pros and cons here. This one gives more freedom, but can also, of course, make the job of making a good robot much more complex. Okay, so that was a little bit about how to optimize bodies, and now I'll talk a bit about how to optimize controllers. Again, there are very many ways to do this, and I won't be able to talk about all of them, but here are some examples. One way we can represent and optimize controllers for robots is by using neural networks, where we can consider that we have some sensor input for the robot, for example, touch sensors on its legs as inputs, and outputs are a control commands for the robots, like how it should move its motors. And an evolutionary algorithm can search for the best possible way to connect this neural network, the best possible parameters for it, to control the robot as well as possible. Another and a bit simpler representation is to use some sort of oscillatory pattern to say that, and then we can specify, for example, that we want our robot's leg to move like this curve. So we want it to move in a certain pattern up and down. But we don't know exactly the parameters of that curve. So we don't know exactly when it should start to lift its leg, how long it should keep it lifted, when it should start it going down, and so on. And those parameters we can allow the evolutionary algorithm to try to figure out. Again, we see here that there's a difference here in how much freedom we give to evolution. With a neural network, you can have a lot of freedom to explore different control patterns, but that can also be harder to figure out. But with a more simplified oscillatory control, we can limit the range of freedom, but also then make it more feasible to find good patterns more quickly. A final way that's a bit different from this is what we see above here with embodied control elements. So this is an example of a soft robot built from these voxels, kind of like Lego bricks, where the different colored voxels have different predefined actions. So some of these expand over time, some of these contract, and that can make them. So based on the way that we put this together, the robot will move in different ways, and then the control and movement of the robot will emerge from how we put the body together. So there is a very tight coupling between the body of the robot and the control. And all of these can basically be with or without sensor feedback. So sometimes we want to try to give some information from the environment to the robot to allow it to modify its control. Other times we have a more fixed control where there's no feedback from the environment to the robot. But more and more we see that experiments are using some sensor feedback because it can definitely help when the environment gets more complex. We need to be able to get some feedback to be able to adapt to, for example, the hills or bumps in the ground. So. Okay, so I thought I'd just also show an example of how a direct versus indirect encoding can look in the case of the control. By giving an example from neural networks. So there was a tutorial on neural evolution earlier this week, so I won't spend too much time on it. But neural evolution is the idea of optimizing a neural network with an evolutionary algorithm. And in the case of evolutionary robotics, this neural network is usually the brain of a robot like this. So we put our evolved brain into the robot, see how well it performs its task, and give it a fitness based on how well it performed. And then that fitness is used to keep driving the evolution forward towards better and better performing robots. And these neural networks can also be, like the robot bodies we saw before, directly or indirectly represented in our evolutionary algorithm. So direct representation would then mean something like this, where we have a genotype is a list of numbers, where each number represents one of the possible connections in our neural network. And we can very quickly then decode this list of numbers into a neural network that controls the robot, but it produces weights for our different connections. Now, again, as before, this gives us a very clean and simple mapping, but it also doesn't give us freedom to explore all sorts of neural networks. And indirect encoding can help us there. And an example of indirect encoding for neural networks is the hyperdeep encoding, which won the Paper of the Decade award. So I won't go into too much detail on it, but instead encourage you to read that paper. And it sets up a very smart indirect representation for neural networks using something called a CPPN, this one, a compositional pattern producing network. And what the evolutionary algorithm optimizes in this case is this CPPN, which becomes a sort of a rule or a recipe for building the neural network that we're building in the end. So here's how it looks like. The thing on the left there is the neural network that's going to control our robot. And for each of the connections in this neural network, we ask the CPPN, how strong should this connection be? And then the CPPN evolves to find better and better recipes for building these connections. And because of the way that the CPPNs are set up, we can ensure that we get some beneficial properties in our neural network, such as the symmetries, regularities, and so on, that we often want to simplify the design of neural networks. And the end result, this is from work by Jeff Bruin and colleagues, the end result is that if we follow, if we use hyperdeep, or in general, if we use these indirect or developmental encodings, we often end up with neural networks and also robot bodies that look more like this on the left here, where there is repetition of structure, symmetry, and they look just a lot more systematic to us. And they can also be beneficial for the robot's functionality because they allow us to solve a problem once and then reuse that solution many times in the robot. Whereas if we use an indirect or a direct encoding, where we optimize each element of a robot or its brain independently, we end up with something more chaotic like this on the left, because each of the connections in these networks here are optimized independently, whereas here they are based on this recipe that we have. So to summarize this discussion of representations, we looked at two main types of representations: direct ones, which are easy to work with and can be faster to work with if we know sort of what we want, but just want to adapt it a little bit. And indirect representations, on the other hand, can be very scalable. They can allow us to find solutions that we haven't really thought about because we didn't know exactly how to set up a neural network or a robot. And they can also give us regularities, symmetries, and repetitions. So let's see one final example of this. Again, this is from work from our colleague Frank. He tested direct and indirect encodings for building these modular robots. So on the left here, you see the best robots that were optimized for walking with a direct encoding. And you see that it uses all sorts of different design elements and doesn't have any sort of way to be able to benefit from reusing knowledge or reusing information. But here are examples of two different indirect encodings that Frank experimented with. And you see that here there's a lot of reuse of patterns. So we see reuse of the design structural elements of the robot, but also reusing how these elements move. So you can figure out just once that it should sort of move like a wave and reuse that across the robot to get a more efficient solution. All right. So that's the end of the most introductory part. Are there any questions so far about the basic elements or representations? Now we will move into the next segment here. What's the question?
Yeah, I have quite a simple question, but like, how was the genome, like, where is that coming from? Like, how do you initially begin with that?
Yeah, that's a good question. How to initialize the genome. So probably the most common is just to randomly initialize it, so that you start with very bad robots in the beginning, and then within some ranges that you know make sense, and then they will get better and better over time. If you have some ideas about a good one, you can insert them also into the population. It's called seeding the evolutionary algorithm. So you can start with something that makes a bit more sense.
How many inputs and outputs do you typically have in the? Yes. How many inputs and outputs do you typically have on these networks with hyperlinks or with direct encoding with scalability?
Yeah, so how many inputs and outputs you have in the networks that control the robots? And so for most evolutionary algorithm experiments, the behavior of the robot is relatively simple. So then we have relatively simple and small neural networks. There have been experiments with scaling up the evolution of neural networks to much bigger sizes. And then the indirect encoding really helps you because then the CPPM in particular can allow you to have a more or less scale invariant neural network. So you can use the same CPPM to build a neural network with 100 or 1,000 different connections. So then you can really scale. But for most evolutionary robotics experiments, since the behaviors are relatively simple, the neural networks are not too deep.
And you have hidden units as well.
Yeah, sure. Yeah. Yeah. So
how many parameters do you have in hand?
In the neural network?
Yeah.
That's a good question. I'm not sure exactly how many, but so that it comes a little bit down to how, I guess it depends sort of what sort of robot you need. So if you have predefined a robot body, then maybe you know a bit more about what it can do and what are its inputs and outputs. And it can be natural to have get bigger neural networks. But if you want the body and control together, then things get quite a bit more complex. And then it's likely that you will struggle if you have too complex neural networks. Yes.
So, how to put this. So what's changed in the last 25 years of evolutionary robotics since the direct encoding of Lipton and Pollock and the indirect encoding of Hornby and Pollock and using health systems?
What's changed in evolution robotics in the last 25 years? Very good question. Kiri, you have been in the field longer than me, maybe you have better ideas of the changes.
Consider thinking, especially on indirect encodings and
Well, both direct and indirect encoding. I'm trying to get a sense for where the progress has been. I mean, everyone uses a different neural network, different model joints and behaviors. I mean, it's actually more than 25 years. If you go back to Stensb in '94, right?
yeah,
If it wasn't constrained to be turned into a real robot, there was always a lot of freedom to make up the representation, but there seems to be a kind of fundamental limit on the complexity of the creatures that we're creating, and that doesn't seem to have changed.
yeah. So I think we might see some more examples during the tutorial. We can try to get a little bit back to it and see if we think many things have changed. I think that's also an excellent start for a discussion on like what are the limits and where can we go. I think there's maybe not been that many changes, or people are still using health systems. But there's been a lot of work on this hyperneat and using CPPMs, and that's been very popular. But I think we can come back to that also. I don't know if anyone else in the Bruin also wants to comment on that, but especially on those interesting colleagues, that people seem to kind of stick with some popular ones, and there's not that much variation. Well, let's have a look through the examples, and then we can get back to that in the end also.
Yeah, I can also briefly add there's also a comment to the back. One thing that has also become popular, especially in the last 10 years, are these illumination algorithms or quality diversity algorithms that can find many solutions at the same time to a certain problem. And then you can, in some ways, get better at adapting because you have a population full of solutions adapted for a little bit different circumstances. So, for example, adapting the damages to a robot body and so on. Let me see, something happened, I think, to the Zoom here. Not quite sure if we are still sharing, but let's have a comment in the back while we figure out. I don't believe it's currently sharing screen.
So, kind of with all the building blocks, like genome encodings and the bonds. And my question is like, if they are looking at the research space and basically trying to solve the goal, how can we, are there any techniques we can like to enforce or like shape the research space so the our robots can evolve into more like expected shapes or expected bodies, or we can like more control that design, or we can like, I don't know, teach them to solve the problem which are more derived, like maybe that is like super science fiction example. But for example, I want to send my robots to Mars, and I want them to learn to mine the rocks and the next generation and like learn it for like for human
yeah, let me start with this last part first. So, yeah, to solve more complicated problems, they're not that often done in evolution robotics, but one way to do it is also done in reinforcement learning is to use what's called curriculum learning, where you set up a simple objective at first, and have the robot to reach that, and then once they reach that, you can set up more complicated tasks that can build on top of the first one. And you talked about also how to constrain your representations to the signs that you think are sensible. So that's quite a lot up to you when you set up the encoding of the robot. So when you decide how are these rules from turning a genotype into the robot, then you can enter constraints in there, like saying that you want to have symmetry, for example, by saying that the left hand, or you build the left side and copy it to the right side. So that's the most normal way to enforce constraints about movement. Okay. I think we have to move on to the next part, and we will be discussing as the control of leaders.
Thank you, Kai. It doesn't have focus. Let me just check that. I am going to talk about the challenges of evolving body and control together. So when optimizing a robot, you basically have two components you want to optimize. One is the morphology or the body of the robot, and the other is the control of the robot. And this can lead to two different search landscapes. I like to see this as two different search landscapes rather than just another dimension added to the search landscape. And this is because a representation you use for a morphology might be completely different than the representation used for control. So a search algorithm that works well for a morphology might not work at all for a control in this case. So this leads to two different search landscapes, and this might eventually lead to early stagnation or early loss of diversity. To visualize this, so let's say in an evolutionary robotic setting, you start off with the parent robot, and this creates two offspring robots. The one at the bottom is very similar to the parent robot, so this causes that it has very close to optimized control because it has already been optimized for the parent robot, and it performs better than the top one. The top one might be a potentially better robot than the bottom one, but it requires completely different control. But because the control already assessed for the parent robot is matching for the bottom robot, this will perform better than the potentially better robot. So within evolutionary algorithms, there is already a phenomenon called the local versus global optimum problem. But in this case, it adds a new problem in that this potentially better performing robot performs actually worse because it doesn't have the optimized control. So there are several methods in trying to deal with this case. One method is to enforce diversity in your population. So let's say in this situation, again, you end up with these two robots, with these three robots, but the top robots, it's more it has more innovation, it is more new to the other robots. So in this case, you might want to keep this robot because you want to protect the innovation. Another way to enforce diversity is using quality diversity. This is what I'm going into now. So quality diversity is based on what we see in nature. In nature, you have this huge set of living organisms that all of them are good in their own thing, but there's not one organism that's good at everything. So you have animals that work well in winter environments, or you have just a very diverse set of animals that are qualitative in their own way. So you create a diverse set of high-performing solutions, and this way you want to have both the quality and the diversity of solutions intact. Okay. So you select the best and diverse robots, and there are some examples for this. One of them is a novelty search with local competition. This means that you select on the novelty. So again, in this case, you will select the most novel robot. But if you have eventually robots that are similar to each other, they will compete with each other. So in this case, if you have these three robots, you will keep this one because it's the most diverse, and these two will compete with each other. So in this case, you will have a quality robot in this population of two, and you will have still a diverse population because you will keep this diverse robots. Another technique is called map elites. So in map elites setting, you want to have multiple diversity measures. So let's say you want to have a set of robots that is good at moving forward as fast as possible, or turn as fast as possible. So there you have want the robot that is good at moving forward, but you want either big robots and you want small robots. Then you can create a map which has certain diversity measures, and for every diversity measure, you will keep the best robot. So initially, you will start with a solution. Let's say in this map, you have on the vertical axis the percentage of bones of the robot, and the horizontal axis the percentage of fossils built. You will start with the robot. You will do some mutations on the robot, and it will change the morphology. You will test how much where in this map it belongs to, and in this location of the map, you will compare it with the best in that location, and if it's better, you will replace it. So in this way, you will generate a map of elites. So you will generate a map of diverse solutions. In every location of the map, you will keep the best solutions or the elite solutions. The challenge here, however, is how to define diversity. So let's say you want a robot that moves fast as far as possible, and you want a diverse population. Well, how do you define diversity? That is a challenge here to see. So up to now, are there any questions about keeping diversity in the population of the robots of evolutionary algorithm?
Yeah, is it, okay. Yeah.
Mm-hmm.
Is it too primitive to just evolve the morphology and then make some kind of selection on them and then train their networks or something? And depending on the outcome, you select the morphologies that work best.
Oh, that's a great question. It might be related to trying to differentiate evolution and learning. So in this case, you will evolve the morphology, and within you would learn the robot over a lifetime to optimize their control, and that might be what I'm going to talk about now. So it's a great question. I will continue on that. So another way to try to deal with the control and morphology evolution is to separate them indeed. So you would start by an evolution loop that would evolve the morphology of a robot, and every morphology will have multiple trials to try to find the optimal control for this specific robot. So evolution, the evolving their morphology is usually an evolutionary algorithm. It can be other optimization algorithms, but it's usually an evolutionary algorithm, and then the lifetime learning algorithm for the control of the robots. It can also be an evolutionary algorithm. Other famous methods are using Bayesian optimization or reinforcement learning. This depends on what kind of control you are using for the robot. So one example is to learn outside of simulation. So you would simulate certain types of robots, and then to assess them in real life, you would build them and then learn, let them learn the control in an arena. Then you would pick the best controller parameters it has learned, and then continue evolution with those parameters. This also shows why it's important to evolve the morphology and learn the control other than other way around. If you want to do it in real life, building a robot, it takes maybe a day or half a day to assess them, to build a control. It takes maybe 30 seconds, 40 seconds. If you would do it the other way around, you would have many less, much fewer possibilities to assess the robot. So this way, the new robots will have more chance to find a more optimal control. So again, in this setting, this robot already had the optimized control, and this setting, this robot will have more tries to find its optimal control and possibly perform better than the other robots. And this has shown to work quite well. So in this setting, in this graph over here, you mostly have to compare the red line with the green line, which is purely evolution, so no learning involved, and the blue line, which is the performance after learning. And you can see that over generations or over morphology tried, the performance indeed increases much more than without learning. However, it is important to know how to compare the two situations. So in one case, you might want to compare on generations or on morphologies evaluated. And this makes sense if you want to do it in real life, for example, where building a robot takes half a day and evaluating a robot takes maybe 30 seconds. But in a simulation setting, it's actually the opposite, where building a robot takes maybe 1 millisecond and evaluating a robot takes 30 seconds. So in this case, it might be more important to compare on function evaluations. And in this sense, you can see that the difference between no learning, which in this case is the green line, and learning, which in this case are the blue and red lines, is less. So when you compare morphologies evaluated, the difference is much bigger, but when you compare function evaluations, it becomes much less. But again, if you really want to evolve real robots, it makes more sense to compare morphologies evaluated, because creating a robot takes much more time. Do you have a question?
Yeah, sorry, but you said this happens in.
Oh.
Can we use this one for the speaker?
Sorry for interrupting, but in the beginning you said this happens in a loop. So
Yes.
I was just wondering, and maybe I missed that part. So after the optimal control is sort of like figured, selected, how does that feed into the selection of the new morphology?
Yes. Sorry, I will talk like this because I hate this on my iPad. So I will get back to the loop. Yeah, I know, but the first I had to like prefer this. So in this case, so in the evolution loop, you would create a new morphology, and then this morphology will learn its optimized control. And then, so you can see this as maybe a certain number of trials with certain number of control parameters. So let's say you want to try 100 control parameters. In this case, you would pick the one which is the best of those 100. So this will be the fitness of this morphology. You can also inherit the control parameters themselves. What I will get into that later. So initially you will have the fitness that is the best performing out of those 100 trials, and you can also inherit the control parameters, but I will get back to that later. Don't know if that answers your question.
Sorry, I'm still not clear how that helps with the selection of the new morphology.
That helps with the selection of the new morphology. So in this evolution loop, there is this thing called survivor selection, and this selects the best out of the population of robots. So if you create, for example, 100 new robots, all these 100 new robots go through learning, and then you pick the 50 best. And you do that by the fitness value, which is the best performing out of those learning trials.
Can I add something to clarify?
Yes.
So maybe I help to
Microphone.
Sorry. Thank you. So maybe helpful to realize that all those evaluations, morphology is set, and only the brain is improving, hopefully, okay? They are not fitness evaluations. So the fitness of the morphology is only evaluated after the learning is finished. So that's a very important detail on how two processes are interacting. Okay? So a lot of things can happen with the brain while the body is already not changing. And the fitness will be only after the brain is optimized for this.
Thank you for the clarification. So yeah, so learning can improve the evolution of robots. Now, one thing that is important to note is you can use the learning just to assess the fitness of the robot, to improve or decrease to improve the fitness of the robot, but you can also inherit the controllers, and there are multiple ways to inherit controllers. I have here 3 ways. So let's say you have a parent robot and it has an initial control. So this is the control parameters before learning, and you have a learned control. This is the control parameters after learning. Well, how do you initialize the control of the offspring robot? There are 3 ways that I have highlighted here. One is called the Darwinian inheritance. So this will cause that the initial control of the offspring is the initial control of its parents. And this requires a mapping between the initial control of the parent to the initial control of the offspring. There is a Lamarckian inheritance. In this way, in this sense, the initial control of the offspring is the learned control of the parent. And this therefore requires a mapping between these learned control and the initial control. You can also completely randomly initialize the controller. So this is just a random initialization or a random inheritance, which is also possible. So I would also like to mention one of the problems between controller inheritance is mismatch between the amount of sensors and actuators, so the amount of things the robot can move. So let's say you have a controller, which is a neural network, and as input, you have all its sensors, and as output, you have all its actuators. This parent robot has 2 sensors and 3 actuators. This offspring robot has 3 sensors and 1 actuator. So the neural network controlling the parent robot will have a different number of input and output neurons than the offspring robot. So this creates a problem to inherit controllers. So how can you do that? One way you can do that is to store an archive of best controllers per input-output pair. So you would, again, based on the map elites algorithm, have on the one axis the number of sensors, and then on the other axis the number of types. So if you number of actuators. So I think where's the other microphone? Yeah, I'm sorry, I really don't have it on my head. So let's say then you create a new robot and you look how many sensors and actuators it has, and then you look into the map which robots have the best control for this number of sensors and actuators, and then you inherit that control. You can also inherit the genotype of an indirect encoding. So again, for a neural network, you might have an indirect encoding creating this neural network. This way you can inherit the indirect encoding genotype instead of just a neural network. This will, however, probably not work for the Lamarckian inheritance because you cannot inherit the learned parameters. You can only inherit the initial parameters. You can store all possible values of a robot's genotype into one gene. So let's say a robot can have a maximum size of 10 by 10. You store all parameters for this out of this map and just use the ones you need to use. Another way you can, for example, have only one controller per actuator. So you can reuse controllers. You can have one controller, you can have 2 controllers that the actuators can choose from. So this was about evolutionary evolving body and control together. Is there any questions to this point?
Can you put that on mute? Does it sound all right? Yeah. Yeah, okay. So I will talk a bit about how we can build these robots and some perspectives on building blocks. So so if we try to imagine a continuum where maybe I can use the laser pointer. Where on the left you have virtual creatures, so they cannot really be built in the real world. And on the other end, you have robots that are fully functional in hardware. So we've seen so many examples of different robots on this spectrum, and yeah, for example, one nice example here is this Lenya framework, which is purely like in a virtual grid. And then we can see like, yeah, we have this seminal work of Carl Sims, the virtual creatures, and some other types of creatures. So they are kind of assembled with blocks, so they're kind of flexible, but not necessarily possible to make in the real world, but then maybe not so far away either. And then there's more like approaches that are resembling modules that can also be instantiated in the real world. So at least in theory, you can make these robots in the real world. So maybe like still in the simulations, you take more freedom and you can like make long chains and like do things that are maybe not so practical to do on the real robots. Also very popular are soft voxel-based robots, which are there are good simulators and frameworks for this. They have been very popular to use for evolution. But in terms of actually producing them, there's still a way to go to make like big practical robots, but it's in theory possible. And then the other aspect is that was like how can you build the robots, but now it's like how do you evolve the robots? So that's also like I try to picture that on a continuum where like on one hand you do evolution in simulation only, and there is never going to be a physical robot in the end. Whereas at the other end you do evolution in hardware only, so there's never any simulation model on it. And maybe what's more popular is to do something in the middle. So you do evolution in simulation, and in the end, you manufacture the end results or some results from that process. There's also been some interesting approaches. So, well, it uses evolution, but in a bit different way, where you have like this process where you evolve a solution, you test it out in the real world, and then you find out there's some mismatch between your simulated model and the real world, and you might use this sensory information to update your internal models and do more simulation before you start using that in the real world. But why do we need to do real robots? I mean, we can just explore in simulation, and that can be quite interesting. It can give us some really nice insights. You can kind of do biology in a way with virtual creatures, like all these discovered species in Lenya, which is really interesting. And you can, for example, try to look for connections between, in this example, there is like the connection between the complexity of the environment and the complexity of the robot bodies that are evolved together. So yeah, and like, I mean, even if these robots are not real, they can still be used to study embodiment in a way, because we are like simulating bodies. So you will be able to get some kind of effects that you can study. But a very popular approach has been this validation and production of the robot in the real world in the end. So that kind of, in a way, it's kind of the best of both worlds, because you can do very fast iterations, very many trials, and you can get good results. And then you make those results that you like. You can make them on real robots platforms, but of course that will take some more time. So that's what you do in the end, in a way, or like when you have a robot that's ready to be deployed for a real use case. So I think maybe so we've seen many proof of concepts on this, but if you have good examples of evolutionary robotics actually being used in say a real setting, of course I'm very interested in hearing that. So it's still a field that's very like on the proof of concept stage, even if it's been 25 years. Here's one interesting, so this everyone knows, like the Golden project, which had that was 2000, I think, right? Very interesting results from that one. Here's something a bit more recent. where like the shape of the robot legs were evolved and then put on a real robot. The problem, though, is the reality gap. So this is a challenge in evolutionary robotics in general, where like the control system of the robot, it looks very good in the simulator, but when you try it on the real robot, it doesn't actually work that well at all. So like, I mean, it could be like small deviations, or it could be like the robot just doesn't move. This is kind of even amplified when you also evolve the morphology of the robot. So there is even more things that can go wrong in the simulation or like be exploited in the simulation. So that the end results when you make a real robot out of it is not that good after all. But there may be some ways to tackle that. And so one thing is this thing now called domain randomization from the RL community, but we also call it like injecting noise in the simulations. So that's one thing you can do. And you could also imagine, like Egge showed in this video earlier, that you have some learning phase going on the real robots so that they can kind of adapt to the new environment, the real world that they're in. And then the final thing you can do is to just evolve in the real world. So that's here's one example from our lab where we evolved the shape of this robot, like the length of the legs of this robot, and we investigated them in an evolutionary setting if the robot would end up with different robot shapes, like the length of the legs, depending on which environment it would be in. So it could be like walking on different surfaces, like different carpets, or it could be having different supply voltages to the motors. And it turned out that it did actually get some different behaviors from that. Here's maybe the one example that has like most freedom in a way in the like real world evolution. So there's also some other interesting projects like this R project that also has a lot of freedom. This one was maybe first with doing, I'd say, I think it was 10 robots over 10 generations. So that's maybe like how far we are in terms of doing quite free robot evolution only in the real world. So modern free robot evolution. So some examples of these building blocks. So some are shown on this axis, but there's a lot of different ways you can do this, and a very popular one has been the voxel-based robots. So there exist some nice, easy-to-use simulators for it, both in 3D and 2D, and you can have these very nice kind of investigations. Then it's a bit kind of soft material, so there are some things that are not so easy to design with a typical engineering methods. So it's a good example of, or like a good candidate for something you could evolve the shape of, and you can see this interesting effects on how these body shapes can expand and contract, and you can see nice interactions and effects. Another approach that's it's a bit more like, say, typical traditional engineering is to have like modules that you can assemble together. So these are like much easier to transfer to the real robot, and you can reuse these components, so you don't have to like waste a lot of materials every time you make a new robot morphology that you want to try. And then usually you can have like some static joints, or you can have rotational actuators, or maybe some translational actuators, and so on. Of course, still it quickly becomes quite much work if you want to have very many of these actuators, and they also fail now and then. So it's quite a bit of upkeep to keep such a library of modules running. Here's some other building blocks. So we have been using some Lego bricks, and I know other researchers have been using that as well. So in that case, you have a kind of like a finer granularity. You can build almost like anything. maybe like you have some discrete steps on how long your legs can be and so on, but it's quite flexible. It takes a bit longer maybe to build them, and it's something that you definitely then have to do manually. So in the case of the modular robots, you could maybe imagine that these robots could be self-reconfigurable, or there could be a robotic arm that puts these modules together. Maybe technically also with Lego bricks, but normally then you would build these robots yourself. But totally reusable, so that's a very good property. And then there's the fully 3D printed approach. Or yeah, so like you can, like in this Bruin project again, you can even 3D print the joints and like the legs and things together. If you have electronics printers, you could kind of incorporate that as well. There's not been so much of that yet, but might come in the future. Takes a very long time to build one robot, and yeah, you would have to throw this morphology away if you plan to kind of continue evolving. So that's maybe the disadvantage of that, but you can get a very nice, fully custom robot from it. So I think like trying to summarize that a bit, like you have to try to choose your platform depending on what kind of research questions you have. So if you want to do a lot of sampling, a lot of evolution with large populations, type of alive biology type of evolutionary research, then it's maybe good to at least start in simulations, because it will take a long time just to get 10 generations going if you do full real world evolution. But it's definitely possible to do evolution also on real robots, and then you get the bonus of getting kind of the full rich interactions of the real world. So there's a lot more richness to your evolutionary setup in a way. But you have much problems with things breaking and lots of engineering challenges and so on. And if you're doing simulation, you can just do any kind of crazy things. You can test out all possible walking patterns without being worried that your robot will break. Because like if you do that in the real world, your robot will definitely break. Yeah, so, well, I think I mentioned this earlier on, that one can, for example, do experiments where you try and see if evolving in different environments gives you different robot bodies and different control patterns. Surprisingly enough, it's not so easy to see this. So I did a lot of experiments with some modular robot setup, and no matter how I changed the environment in a way, it would still end up in similar robot bodies. So they will look like snakes anyway. So that's kind of funny. So there's things that maybe hinder you before you can actually see these nice effects that you want to see in the beginning. So that there could be like some bias in the encodings, or it could be this problem that Eggy talked about, that the search stagnates to a certain morphology, and then it only has like learning to play with. And also, of course, you have to be good at specifying a challenging and rich environment. Because, for example, if you typically people evolve something that's to locomote on a flat plane, so move as fast as possible on a flat plane. And well, in a way, then it's maybe not so strange that you get a snake as the result, because it can just roll over the plane, and it might be a perfectly nice solution for that type of environment. So if you really want a four-legged robot that climbs around, then you need some environment that it has to learn that in or evolve that in as well. Something about simulation. So there's a lot of physics simulators. So definitely the most common approach is to use these rigid body physics simulators. There's plenty out there, like Physics, Bullets, OD is an old classic, Dart, Box 2D, you can do 2D simulations, then it's even more like fast, so computationally very cheap. And Mujoko is a popular one. And if you want to go with a bit more like interesting materials, you can use VoxCAD or some spring damper systems and other kind of soft simulation systems. You can also do, for example, if you think a bit towards engineering and materials, you can do finite element methods. And like if you want to design some structures that should have like good structural properties. And then there's like high-level wrappers on top of these again. So you have, for example, Gazebo within the robot operating system. You have Coppelia Sim, is this kind of robot-centered simulator, and Isaac Sim from NVIDIA, and game engines that all use this kind of low-level physics library under the hood. So currently, these things have not been very fast, so maybe faster than doing it in the real world. But they've been kind of single-threaded, running on a single CPU. But now we're seeing that these simulations are parallelized, and they can run on GPUs. And people are talking about, like, if you manage to do this in a good way, you can get like 100 times or 1,000 times speed ups on your simulations. I think that has not been really exploited so much yet by the evolutionary robotics community. And if we manage to do that, I think we could see even more interesting results. We could do this learning and have large populations and all that. And hopefully that would get us a bit further in the results. So maybe at the moment there's the NVIDIA Isaac Sim, and there's something called Majoko XLA that have built-in GPU parallelization that could be used out of the box. So I think there's a lot of potential here. But I think another thing that has, hindered the evolutionary robotics community to make like big progress in a way, is that there's kind of no standard approach. There's no like standard library that you can just download and do evolutionary robotics experiments when it comes to the evolution of morphology and control at the same time. There's a couple. So there's this evolution gym here on the top, for example. It's very easy to get started on evolving 2D voxel type, or like soft robots. I shouldn't call it voxel when it's in 2D, but that's a side note. But of course, it's a little bit in the nature of the problem as well, right? Because it's not like a single robot that you want to optimize. You want to explore lots of different bodies. So it's not so strange in a way that researchers have been kind of doing something custom from the bottom up when they were like looking at a new problem. There's also some attempts at doing some kind of like modular robotic frameworks with specified components that others can use, such as the RoboGAN system. Yeah, that's where we are today on that. But I think like since we have this this challenge that like everyone tends to do their own thing. So say that you're a PhD student, you spend the first year of your PhD studies to build a software system, or maybe like another year to build a hardware robot. And you kind of, everyone gets to the hello world stage in a way of evolution of morphology and control. So you get something that runs, but you didn't actually get the time to investigate what you wanted to investigate. So you wanted to say investigate different types of environments. No, due to time constraints, you would have to go on a flat surface, for example, and yes, similar things. So maybe that's why we are like still in the starting phase in a way. Like so maybe we could benefit from interacting more and making efforts at building some kind of common framework or toolkits that make it easier for us to kind of reduce the amount of starting time to do more interesting research on it. And also, like, of course, you have this challenge. So like you set up a very nice environment and you show something very interesting, but then you have only shown that this thing works in your specific environment. And maybe if you think about it, that's maybe not so convincing. So you can see some learning effect or speciation effect, but it only exists in your constructed world. So it would be nice if one could like more easily test things in different worlds or environments as well to make the results more valid. So only one setup. So that's kind of where I'm going at now. So like in the next part, we'll Emma will talk a bit about like our attempt to try to like help build some kind of framework that others could use. But maybe are there some questions up to this stage maybe? So now we're kind of ending the theory part, and we'll move on to a bit of demo and talking around our Unity-based system. Yes, let's see the demo. Okay, thanks. Yes, all of you. Right.
So a provocative question, I know the answer, but do you know of any system anywhere on Earth from any lab that is also incorporates the usage of energy? Or all these robots in the simulator are just happy without using energy, they can go on infinitely?
Yes, well, so before you said simulator, I could say yes, our robot, because we have a real robot.
No, the simulator.
Yes, so in simulation, I mean, there should be values of at least approximating how much energy the robot uses. But in many of our projects, we like try to incorporate that into the simulation, but it hasn't really worked that well, and we ended up like skipping that. And maybe thinking about other proxies like the mass of the robot or something that would, or like number of joints that could somehow say something. It's not really that good, but I don't really see why there should be like it should be possible to get it out if you just know enough about your physics simulator and work a bit on that problem.
Completely agree. It should be possible, and it would make the robots much more realistic, somehow more relevant what you learn. But to my knowledge, nobody is using it. So it's like the whole community is ignoring energy.
I think it's a little bit of the fat plane problem that I mentioned. So like this is something that everyone wants to put that into the equation, but usually it ends up being just a fitness function of walking as fast as possible. So, but definitely that should be something that goes into the fitness function. And I think also in this case, some of the research done by the deep reinforcement learning labs, they do quite advanced reward functions with many components. And maybe there's something to learn from them if you look into like how they made it with robots work with the deep reinforcement learning.
But the problem of including this in, the problem of including this in the fitness function or the reward, and you start creating extra problems as opposed to having this naturally in the simulation world. And it complexify the space in a way that it normally wouldn't happen. If the energy is down, energy is down, and then it doesn't create artifacts, but if you start pushing it into the function,
Yeah, that's definitely a good point. So like if you explicitly tell in a fitness function that you want to reduce the energy spent, so maybe the focus is only on that, and you get robots that just stand still, for example. But yeah, in the case of our real robot, we have like a limited voltage that we could give to the servos. We just turn down the knob on our volt or like a power supply. And then of course it had to just cope with that, so it would try to maximize what it did given those constraints. Yeah, so that's another way of doing it. I think there are some questions over here.
Yes, thanks so much. So I have two questions. The first one is about the robot that you showed several slides ago, the white one in 2x. And you had relatively few sensory inputs. So maybe it would help if you added proprioception, so that you know itself, its own handles, for example, and also some memory. Then maybe that would lead to more efficient robots, and learning faster, more efficient. A real animal. Yeah. And then the second question is about slide that you showed with a really strange looking lake. And then developed with evolutionary algorithms. Yeah. And that reminded me of an equally strange looking antenna that I saw that's also developed by evolutionary algorithms. And I mean, my question is, are they good or are they genius or are they stupid?
Yeah, I think so to take the last one first, I think there are a bit of both in a way. So I think like with this strange looking legs, so that like the reason it looks quite strange is because of a bias in the way they encoded it. they have some control points for those first lines that together we can form a shape. And like when you have control points for spine, they can go a little bit in every direction, but still they manage to do the job. But it's very non-optimal design. So yeah, maybe if you, as we talked about, like put enough things into your fitness function or constrain the maximum amount of there you have, maybe you could get a better design. Yeah. But in a way, also you could see this as a tool for engineers to get ideas and then they can manually like refine the solutions. And in the first case, yeah, there are definitely some approaches that improve progress action as well. So that's also something that is explored, and I think it will it leads in general to more robust behavior. Yeah. Any other question before we move on to the demo part? No? Are you ready with the
Yes.
visuals? Do you want this one?
Yeah. Okay, so hello, my name is Emma. I'm going to do a short demonstration of our attempt at making a framework that others can use to evolve modular robots. So I'll try to go a bit quick. I don't think we have all that much time left. Okay, yeah. So the idea behind our approach was that when you're just starting out with evolving robots, it can be a bit tough to get going. We wanted to create a framework that was easy to get up and running, and that also had the flexibility to define your own building blocks for the robots you wanted to evolve. And our colleague Frank is the mastermind or the developer behind this framework, so all credit to him. But yeah, he wanted to develop this framework to help people get into evolutionary robotics. So I'm going to show off this framework. Last year, we showed how to get the framework up and running. But this year, we instead decided to go a bit deeper and show instead how you can use this framework to design your own morphological components and environments. So first off, I will just start evaluating some random robots just to show you how it works or how it looks. So this is just some random modular robot, the random controller was flopping about and being stupid. But this is running in an executable made with Unity. And the interface that I'm running it through is made with Python. So you can see I'm running a Python script here that starts this simulation. And so what I will be showing you today is I will tell you a little bit about how this works in the background and also how to define your own morphological components to evolve the kind of robot that you want to make. So this framework has been developed in Unity, which is actually a game engine used to develop video games. The game engine uses NVIDIA physics engine, and it uses a framework or a library for that game engine called Unity Machine Learning Agents. And this is a framework developed by Unity to enable people to use the Unity engine for AI research and also for game developing and using AI in games. But this framework is actually very nice because it has a Python API, which is very similar to the OpenAI Gym. It's not called that anymore, but how OpenAI Gym made Python API is. And so it's quite easy to use. And so this ML agent library is an interface that communicates between Python
and Unity. So then you can, in Unity, design your robot components, design your environments, and tune your physics engine, define the fitness function, and then use Unity to create the entire simulation of the robot. Using the MLH's framework, you can then use Python to import or write your optimization algorithm to optimize these robots. And on the Python side, you will then, the optimization algorithm will use a genotype needs to have evaluated, create a blueprint, and send that blueprint using the ML Agents API to Unity, which will then evaluate the robot and send the fitness value or send the information back to the Python interface. And then Python side is then responsible for optimization algorithm and for also plotting data and parallelization. So yeah, our colleague, as I said, Frank, developed this evolving modular robots in Unity framework. And if you want to check it out, there's a QR code here. And then this can then be downloaded from our GitHub. So yeah, just to give you a short overview of how this process works is you have then your, so the Unity has an editor where you can build your simulator. And you also have then the Python side where you develop your algorithms, optimization algorithm, as we talked about, and the ML Agents toolkit, which helps you communicate. But when you have finished developing your simulator, you don't want to keep running it in the Unity editor. So to enable parallelization and so on, you build an executable, and you can then instead communicate with the executable using the ML Agents toolkit to run your experiments. So now I will switch over to the Unity editor. So yeah, I guess I can just before, if you so if you don't want to get into the Unity editor, there is also an executable, which was the one I showed you at the beginning of the presentation. That is already built that you can use, but then you cannot change the components that you use for your robot. So to change the modules for the robot, you have to use the Unity editor. But if you want to try just running it, there is a guide here on our GitHub page. And in the GitHub repository, there are two main components. This is the EMR folder. This contains the Python package. So this is where the evolutionary algorithm is implemented. If you want to change the optimization algorithm, you'll have to modify the Python package here. There is also a Unity package, which you can install after starting a new Unity project. I will not go through how to do that. There is a lot of documentation online, as Unity is used a lot, and there are tons of resources if you look at the game creation resources as well. But here I have a Unity project that I have just started. Only the two things I have done is install the ML Agents package and also install the Unity package that comes with the repository for our framework. And this is a scene where if I play this, we can see a random robot also moving. It contains like two main components, the game manager and the individual. Yeah, here you can see some random robots being generated and moving about. This contains the game manager, which handles the communication with Python side. Right now, it's not connected to Python, but here you can also change the physics parameters and so on. And this is the most important part for us, the individual. This is what spawns the robot that is to be evaluated. And it has this modular robot script attached. And in this modular robot script, there is a list of component prefabs. So these are the building blocks that will be used to create the robots. So right now there's just one module, which is the emerge module, which is the red one you saw when I started it. And we will be adding an additional module here. So to create a module, I will create a prefab and call it a life module. So this will be like a blueprint for a module that you can use to build your robot. You can double click that to edit it. And then when creating a module, there is a module script. So if we search for that, we can add a module script. And to build our module, we need to fill in several pieces of information for the simulator here in the references section. So first of all, we will just make a random shape. I will just make it a sphere. Just here you can do any shape you want. So right now I'm doing a sphere, just for simplicity. So this will be then your module. And to enable physics simulation of this sphere, you need to add a rigid body, that means the physics simulator will simulate it as a rigid body. And we also need to know where this should attach to the previous module of the robot. This is just for connection site to parent. So this needs to connect to a parent module. And this parent connection site determines where will this connect to the previous module of the robot. So we can just have that at the bottom of the module. And we also need to have a joint that will connect this module to the previous module. So now add a joint. And for now, I will just have no movement. So if I set all of these motion parameters to locked, it will just be statically connected without any movement. And this joint will then need to go into this attachment joint slot, which is how the framework knows that this is the joint for attaching the module. In addition to this, we will also need, if you want the simulator to make sure no modules are colliding, we need to also add a bounding box for collision checking. And this bounding box should not collide with other objects in the scene, and therefore we have to enable this trigger. One last thing that needs to be done is to put this on the module layer. So this is a layer where all the spawn modules should be placed. So now we go back to our individual. We should be able to drag and drop our newly created module here. And if we start the simulator again, this module should also be used in our robots. Oops. Yes. Oh yeah, just this collider box needs to go into the collider box. It's not here. There's the risk of doing things. Maybe it doesn't. I will try to just add the connection site for the next module, because maybe it needs to have at least one connection site. So this list of connection sites here, you can add then places where child modules can be attached to this module. Yeah, so let me just use my backup module. Yeah, so this is basically exactly the same. We have the sphere with a rigid body and a joint, and connection site for the parent, connection site for child module, and the collision check box. And then you can see the module is then added to the newly generated robot. So this is just a static sphere, but perhaps you want to add a little bit more functionality to this sphere, for example, by extending it to move. So make the sphere rotate like this. Then we use this configurable joint that attaches this to the parent, and we can add, for example, angular X motion. And we have to choose what axis we want it to rotate around. So I will do it around the y-axis, which is this green arrow. So let the sphere rotate like this. And we can also add some more connection sites if you want. So let's add another connection site. So the module that is being added will always be added along this green arrow shown in the editor here. If you make a connection site, make sure this green arrow points in the direction you want your new child module to go. And here there is a list of joints, which is where the actuated joints need to be added for them to be included in the simulation. So now that we have enabled angular X motion, and we can add our joint here so that this module will be actuated. I think we should also add a little visual cue just so that we can see whether our module is actually rotating. And we also need to configure the strength of our joint. And we do that here. Now we have adding angular X motion. So we need to find the angular X drive. And here, this is controlled by a PD controller. So here you can add for spring and damper coefficients for your joint. And also the maximum force that you can apply. So now we can try again with this new activated module. We can keep moving. Okay, so this was this was how to create modules using this framework. I think I'll just move on since we're almost out of time. You can also easily add obstacles in the environment. For example, by you can add so 3D object cube, and that will appear with the simulation of the robot. I can see there's an obstacle in the way. And you can also create scripts to generate these obstacles along your entire surface. So I can just show you. It's very easy to create scripts to spawn obstacles. You can just instantiate them and send in the position. So if I add this. Spawn obstacles. And I have a very long cube here that looks like this. I will spawn in. And let's say we want 100 of them with a gap of 0.5 units. So what I think is very great about using Unity for robot simulation is that you can very easily find a lot of resources online on how to modify the environment and use the Unity engine because it's so used a lot for game development. And we're out of time, I guess. I'll continue for a little bit. If you need to go, then just feel free to go. Yes. So.
Maybe we can wrap up the design stuff and so on.
Yeah.
And also because you can stay in to see any part.
Yeah. If anyone wants, if you have a question.
Yeah. So my question is, because we have. So from like, it's maybe more outside technical question from like software engineering perspective, but the key components here. So this looks like functional engine, which is environment, community engine. My question is how much those two parts are put together. So how easy it would be for me to take the evolutionary engine and connect it to another Python or another engine. Like is there API between this like between Unity and EMR, or is there like how much are coupled together? How easy is to separate those two components?
Yeah. So I think whatever you implement in Python would be you could easily reuse. You can couple in any algorithm you have already implemented Python to use the Unity engine, but the other way around would not be so easy. So because this API then communicates between Python and Unity, and so yeah, basically you can reuse the Python part very easily, but the Unity part is not as easily coupled to something else, and you'd have to do it through Python. So I'll just wrap up with the final slides. Yeah, we just had some examples of what we have done, but I think we've already shown quite a lot. This is some modular robot project by a master student. Most interesting is that we can revolve these two guys, comparing different controllers. And this is just testing the RoboGrammer modules in this framework. We also used it to simulate some centipede-like robots to investigate walking patterns of centipedes. And yeah, I just want to show this. What I think is very great about Unity is you can easily create visualizations of what is going on in your simulator. So here you can see two robots with different like springiness in their joints. You can see that one bounces a lot more than the other one. It's just a position plotted there at the bottom, as it goes. So yeah, I also just wanted to say that the reasons to use Unity is that it's very easy to set up, a lot of documentation, and video games might be some stigma around using video game engine, but they also deal a lot with physics simulation. So I think we could learn a lot from each other. And it's also very fun to work with. And I guess some of the cons with Unity is that it's, of course, optimized for games. So it might need a little bit of tinkering to get the physics engine to work precisely as you want it to. And yeah, of course, also doesn't run out of the box on GPU. So if you need it to run, won't run with GPU, then all the frameworks might be better. Yeah, try it out. Do you want to do the last two slides before?
I think it will be mentioned later.
Yes, thank you for listening.